Hi everyone, this is Kathleen Quach, and I'm going to continue on with my lecture series about probability theory. This is the second lecture, and today I'll be talking about basic probability and Bayes' theorem. I want to go ahead and remind everyone of what I mentioned in the last lecture, which is what I believe to be the three reasons why probability theory is confusing. And they are that you may not be counting properly, or you may not know the definitions that are the fundamental building blocks of probability, or your intuitions are wrong. So hopefully I've addressed these two items in the last lecture, and today we really want to focus on this last issue right here about intuitions about probability. So this lecture ultimately is about the meaning of probabilities. So first I have some remarks, they're really cautionary remarks, and it's that probability theory is not the same thing as statistics, okay? Probability theory concerns itself with math, and in particular mathematical models, where statistic tries to relate some real data to a mathematical model and make some judgment about it, about, for example, how good the data matches the model, for example, or whether or not to reject a model based on reject a model based for hypothesis testing, for example. Okay, so let me give you an example. Say we have a mathematical model in which the probability of encountering land on the surface of the Earth is 0.25, and the probability of encountering water on the Earth's surface is 0.75. So this is our model. We are assuming without question that these values are what they are. We are not assessing the realness of these values at all, the validity of these values. We're just assuming that that's what they are, and then we're using this model to do more math. Statistics will have measured real data and try to figure out how much they match these values right here and what that means if it's not so. We are not there yet. We are not in statistics. This is just probability theory. Okay, we are setting ourselves up to further understand statistics later on as the weeks go on. The second question that I need to address is, what are we modeling? We are not modeling events or phenomena that we know as or called or referred to as deterministic. Deterministic processes are ones in which you, when given a certain input, will always get the same output. So machines and algorithms are a good example of these. If you put a value into an algorithm, it should always repeat the same outcome. And if you handle a machine the same way, it should act the same way. For example, if you turn on the power button of a dryer, it should turn on. If you press stop, it should stop. That sort of thing. This is not what we're dealing with. What we are dealing with are phenomena that, given a certain output, may not give the same output every time. And that the modeling of the output is what we call probabilistic. There is a certain probability associated with each outcome, but we are unable to definitively determine at any given outcome what the identity of the outcome will be. This is exactly what we're modeling, and a real life example of these phenomena are often, that we all know of, is dice. So you can be throwing a dice in what you believe to do the same way every time, and you may not get the same face every time. It could be a 1, it could be a 5, it could be 6, whatever. So we are modeling probabilistic phenomena, okay? Probabilistic phenomena have some aspect of randomness to it. Okay, so now we're ready to go ahead and talk about basic probability. To illustrate concepts of basic probability, I'm going to be using the same example every time, which is this. I have a honeybee, and this honeybee is foraging in a field. The bee cannot leave the area of this field. For example, let's say there's a force field or some insurmountable net, whatever. There's something that is blocking the bee from leaving this field. It can only explore this field. This field is a metaphor for what is considered a sample space. A sample space contains all the possibilities that you are concerned with. And therefore, the probability of anything in the sample space happening is 1. Everything. And in the sample space, there are certain events that can happen, and all the events that could possibly happen are as follows. This is the set of the events. Remember the set notation with the curly brackets. So the bee can see a cornflower. It can see, let me start over. So the bee, as it's foraging, as it's flying over a field, and it looks down, it can see a cornflower, or it can see a daffodil, or it can see a rose. You can see all these things at once. You can see two of these things because all these flowers are at different heights. Okay, so it's possible to see all these things at once when it looks down. Okay, so remember, it's important that these flowers occupy different heights. They can occur on the same z-axis. The bee is just looking down and seeing whether or not they see these flowers. Okay, so now we're going to talk about the probability of a single event. So in this sample space right here, probability of a single event A, which is this cornflower patch, occupies this area right here. Since this area right here is obviously smaller than the sample space, we can say that A is a subset of the sample space, and therefore the probability of A has to be greater than 0, but less than or equal to 1. Sorry, greater than or equal to 0. It can be 0. Complementary event is everything that is not that event. Right? So the complement of A, this cornflower patch, is everything in this field, this sample space, that is not encompassed by this circle right here. And when you add these two together, the event, the probability event, and its complement, the probability of its complement, then you should get 1. It should encompass the entire sample space. So let's talk about what disjoint events are. So disjoint events are events that have no probabilistic overlap. Okay, so these events occur separately of each other. There is never a point at which a bee will look down and see both these things at the same time. You can only see one or the other. And mathematically, what this turns out to mean is the probability of A union B, so the union of these two events, is equal to the addition of these individual events occurring separately within the sample space. Okay, so just adding these two areas up together is enough to produce the union, the probability of the union of these two events. The more interesting thing, though, is joint probabilities. It's when these two events can overlap. So, for example, we want to find out the probability of a bee flying over this field, foraging, looking down and seeing both a cornflower and a daffodil at the same time. And in that case, what we have here is the probability of A and B occurring at the same time, which, if you remember the nomenclature from before, is the P of the intersection of these two events. And in this example, in this visual example, what we have here is the literal intersection overlap of these two areas right here. So that's the intersection, okay? This is the joint probability. So now that we've talked about joint probability, we can talk about independence. So it's important assumption in these probability operations is whether or not two events are independent. And practically, in this example, what this means is that the bee has no preference for one flower or the other. The only thing that dictates the probability of these events is whether or not a bee physically is flying over that flower. Okay, there is no preference whatsoever to, for example, chemotax towards these flowers. It's simply just flying randomly and looking down and seeing, oh, what do I see? Okay, it's not using any senses. It's not trying to move to one flower or the other. And so if these two events are independent, then what we can see is the probability of the intersection of these two events is equal to the multiplication, the product, of these two probabilities by themselves. So now let's go on to conditional probability. Now that we know about the joint probability. So conditional probability, terminology is A given B. So probability of A encountering a blue flower given B encountering yellow flower is equal to the intersection, which is this area right here, the intersection of these two events with respect to just encountering the yellow flower by itself. Okay, so that is essentially what a conditional probability is. It's assessing a probability of two events with respect to the latter event. Okay? So P of A given B is probability of the intersection of these two events with respect, basically dividing by probability of just this event by itself. Okay? And so that's, and it's to note that this is normally replaced. So if it were just P of A, so if it were, yes, so if you wanted to find P of A, the intersection of, probably the intersection of these two events in general, then P of B would normally be replaced by 1, which is equal to the sample space. Okay, but now we just want to see what it is relative to a given event having occurred already. So let's do some mathematical manipulations to see what we can do with this. So given this expression, let's multiply both sides by P of B. Then what we get is a new equation for the intersection of these two events, which is the conditional probability of these two events of A given B multiplied by P of B. So now we have a second type of equation for the intersection. And we can use this to illustrate that we can use these equations for more than two events. So let's say that a bee is flying over a field and it looks down and it can see all three flowers at once. So that would be the intersection of these three flower patches, right? So there's a rose patch, a cornflower patch, and a daffodil patch. These flowers are all occupying different heights. They can all be in the same z-axis. We can look down and can see all three flowers at once. So we have this equation right here, which is the probability of a bee seeing both a blue flower and a yellow flower. But now you want to see what the probability of seeing all three flowers are. So now that what we can do is we can chain a new event, which is C right here, the red flower, and we can move what we've already figured out to be the probability of the intersection of these two flowers, the blue and the yellow. We can move that to the end and add a new conditional probability, basically a probability of the red rose, probability of C, given that you've already have the intersection already of these two flowers. So you've already have a bee who's already in both a cornflower patch and a daffodil patch. And now you want to find the probability of seeing all three, given that you're already in two of them. Okay, and so that's how you calculate that. And there's just another note that you can write here. Sorry, so this is just to remind you that you can also calculate the intersection of all these three events just by multiplying each of the individual events, probably the individual events. Okay? So I went through that pretty quickly. Please review them if you think you have to. These are going to be understanding these different types of basic probabilities is going to be integral to understanding the next part, basically the derivation of Bayes' theorem. So please go back if you have to before you move on. Okay. So to derive Bayes' theorem, we first need to find two expressions for the probability of the intersection of two events. And just a reminder, the intersection of two events in our example of the bees is the literal overlap of these two patches, okay? So if you recall, we have the expression for the conditional probability which is P of A given B times P of B, okay? And so we can pop that in on one side. We can find the other side of this equation by reversing the conditionality, right? So we can say, all right, so in the probability of B given A, then we can, is equal to the probability of A intersecting B divided by the probability of just A alone. And then if we multiply both sides by the probability of just A alone, then we get this new equation for the intersection of those two events, which is just the probability of B given A times P of A. Okay, so we have what we see here, the inverses of each other equaling to the same thing, which is the intersection of these two events. And now we can take this whole thing here, move it, and try to derive Bayes' theorem mathematically. So here we are. We can remove this part because these two things are equal to each other. We can divide each side by P of B. And then here we have it. It's Bayes' theorem. It's that easy. But what's more difficult, the most difficult part of this is understanding what each part means. So I'm going to go through it slowly. Please take your time to understand. So A represents belief, okay? So A is what you believe, and probability of just A by itself is their prior. This is called the prior. It's your belief before you have any evidence, before you take any evidence into account. B represents the evidence, and the probability of just B by itself represents the strength of your evidence. Your posterior represents this whole thing out here, this whole output right here is your updated belief, which is what you believe given that your evidence. And a good example of this is, say A equals, it represents your belief that there are only white swans in your local pond. And B is the existence of a black swan. So your prior belief is that there are no black swans whatsoever. It's just all white swans in your local pond. And P of B is the probability that there is a black swan. And so you can imagine that the probability that your belief that only white swans are in your pond will go down given that you have seen a black swan. Okay, so that's just an example. Let's go ahead and continue on with the variations of Bayes' theorem. So there's a common form of Bayes' theorem called Bayes' rule, and it's used for odds or ratios. Odds are basically just ratios, and so if you want to calculate Bayes' theorems for ratios, you simply just take two versions of Bayes' theorems, right here, two Bayes' theorems, and divide them by each other. And that's it, okay? So you divide them by each other. So note that, so we're saying there are two types of beliefs that can happen. Say like you have belief 1 and belief 2, and the same evidence can influence your decision about both of these, okay? So there are two events, you want to divide them by each other. What you can see here is that both sides have the same P of B. P of B, you can remove that when you divide them. And so what you have here is an odds form of Bayes' theorem. So the different parts have different meanings. So this is the prior odds right here. This is how much you believe your belief 1 over a belief 2. This is your posterior odds, basically this is your, basically how much you believe 1 versus how much you believe number 2, given evidence. And so you can imagine if this number is greater than 1, then you're going to say, okay, belief 1 is stronger, and if this is less than 1, you say, okay, belief 2 is stronger. And then finally, this is super important, this is called the likelihood ratio right here. And this is often the influencing factor, this is the influencing factor when you want to use evidence to update your belief. Basically, which of your beliefs you want to pick. Okay? Alright, but let's just use an example. That'll be easier to explain. Alright, so the classic Bayes' theorem example is the Monty Hall problem. Way back when, I don't know when, probably the 70s, I'm not sure. There's a game show in which the host, I believe his name is Monty Hall, asks a contestant to pick a door out of 3 doors. So the rules are, behind one door is a car, and behind the other 2 doors are goats. Okay? Suppose you pick door 1, and at this point you still don't know what's behind it. To add to the drama, after you pick door 1, the host reveals a goat behind one of the remaining 2 doors. And in this example, he picks door 3, and you see a goat. Part of the rules dictate that the host never reveals a car, because why would he want to help you win a car? That's not in his best interest, okay? It's not in the show's best interest. So again, just to reiterate, you pick door 1. You're not told what door 1 is yet, but the host will always reveal a goat in one of the remaining 2 doors. And then you have to decide, should I stick with my original choice or should I switch to door 2? And we can figure out what the best strategy for that is with the Bayes rule. Okay, so just to remind you, this is what the Bayes rule looks like. So you have three beliefs that you can possibly have. You can have a belief that the car is behind door 1. You can have a belief that the car is behind door 2. So these are the C's. Or you can believe that the car is behind door 3. Okay? A priori, before the host opens any door, this is what you can believe, okay? So that's your prior odds. This is your likelihood ratio is, now you need to figure out the likelihood ratio to figure out how to update your posterior. So given the location, which basically comes down to this, given the location of the car, you need to figure out which doors the host can open and if door 3 is one of them. Alright, so let's go do that step by step. Okay, so this is the first one you want to do. So given that the host is open door 3, what is the likelihood that the car is behind door 1? So it could be behind door 1 or so this is what we're given. We're given car is behind door 1. That's what we're assuming. Then in that case, the goat can be behind door 2 or it can be behind door 3. So the number of doors the host can open is 2. And is door 3 number one of them? Yes. So that means we have 1 out of 2 possible options. Okay, so 1 just indicates that yes, door 3 is one of the possible doors that could have contained goats. Okay, so this is, and 2, there are 2 options for which that there are 2 doors that the host could open. That's what it basically means. Okay, let's move on to the next option, which is, let's assume that the car is really behind door 2. In that case, given that what doors could the host have opened? Remember, you can only open one of these 2 doors, right? He can only open one because he's not going to reveal the car in any case. That's just not what he's going to do. In that case, then you have 1 door that is door number 3, that the host could open, and a total of 1 door that he could have opened that was possible. Alright, so let's figure out the last one, which is the probability that the host opens door 3 if the car was behind door 3. And we know, just as a matter of the rules, the host will never open the door if it has a car, so the probability of that happening is 0. Okay, so he will never open the door. So 0 represents the fact that the host will not open door 3, and 1 is that he can have opened 1 door total, which would have been door 2. And so let's go ahead and multiply this whole thing by 2 to get whole numbers for odds, which ends up being 1 to 2 to 0. And if we multiply both these things together, what we get is odds of 1 to 2 to 0. Okay? Which means that you should switch to door 2. It's twice as likely that the car is behind door 2 than it is at door 1. So you switch to door 2. And more likely than not, you'll have a Bugatti behind it. Okay? Alright, so we've been talking about Bayes' theory as a way to update belief, but there is another way to interpret Bayes' theorem. Okay, so just to remind you, the Bayesian interpretation of Bayes' theorem is that probability measures a degree of belief. Therefore, Bayes' theorem connects the degree of belief for something before and after accounting for evidence. There's a whole other school of using Bayes' theorem, and it's called FREQUENTIST. So the frequentist interpretation of Bayes' theorem is that probability measures the proportion of outcomes. Therefore, Bayes' theorem connects conditional probabilities to their inverse. But what this all really boils down to is this, trees. Using trees to plot outcomes, okay? So these are called trees. They're not frequentist trees. They're not usually called that, but I call them that because it's, yeah. Basically, if you're seeing a frequentist use the Bayes' theorem, it involves trees. Okay. So, for example, this is how the trees work. Say you have this branching point here. You can have A, or you can have the complement of A happen, right? So there are only two options. So, given that A has happened, what's the probability of B or not B happening? And then what is the intersection of those two? So that's how this works. It's sort of like a whittling down of outcomes given the step before, okay? And you can flip the trees using this right here, the fact that this is equal to this and that, okay? So that'll be a homework problem that we'll work on. But let's go to talk about Bayes' theorem for complementary events. So when you have complementary events, you can tweak Bayes' theorem to your favor. So this right here is just a property of complementary events. These two things have to equal 1, right? A complement and something in a complement must equal 1. Given that they have the same relative. So like, you know, they're both given B, so that means in the same relative space. Okay, so what we have then is this. So this is the Bayes' theorem, the individual Bayes' theorem for each of these two things. So then we can remove this part and have this whole thing equal 1. We can multiply both sides by P of B. And now we have something equaling P of B that we can use instead of P of B, an expression, that is. So let's replace P of B in another Bayes theorem with this. So this is Bayes' theorem again, but this time we replaced P of B with this giant expression right here. Okay? Alright, and this is just to make sure that we keep everything to one tree. It's just for convenience. But if you wanted to, like if you wanted to find P of B, you can flip the tree and find that. Alright, so here we have this. Let's see, look at an example. This is the classic example that is often used with trees. So here we are. We have a drug test that is 99% sensitive, which means that 99% true positive results for drug users. And then the test is also 99% specific, which means 99% true negative results for non-drug users. Let's assume that 0.5% of people are drug users. The question now is, if a randomly selected individual tests positive, what is the probability that the individual is a user? So let's translate this to tree form. Okay, so we have probability that someone is a user or someone is not a user. And then if, for example, we go along this branch, then we'll say, okay, so given that someone is a user, what's the probability that the test is positive versus the test is negative? All right, so that's what this tree means. Let's fill in the numbers. So we know that 0.5% of all people are users. That's what this is here. This refers to 99% sensitive. This refers to 99% specific. Okay? Just remember that? Okay, so that's what this means. 99% sensitive, 99% specific. And then you can just do simple adding and subtracting, and multiplication to get the rest of the numbers, all right? So this is just 100 minus that, etc., etc. And then you can just use the basic definition of joint probability, basically just multiplying the two individual, you can multiply these two numbers, for example, to get the joint probabilities, which is right here. And then now that you have all these numbers, you can plug them into Bayes' theorem for complementary events. So we have all these things. Let's put that into place. Okay. And then what we have after you plug everything in is this. The probability that someone is a user given a positive test is 33.2%. Okay, so what does this really mean? The probability that someone is a user given a positive test. So say you have to get a drug test for a job, and it comes back positive. And based on that test, your company has to decide whether or not to hire you. And it's only 30% likely that you have. So if you have a positive test, that doesn't definitively mean that you are a user. That's what this means, okay? And it's a very small number compared to what you would want it to be. Like, you would hope that given a positive test, and it was a very, very good test, then 100% of the time it would mean that you were a user. But it doesn't. And so this is not intuitive, okay? You have all these high numbers right here, and it sounds like a great, fantastic test, right? 99%, 99%. That is not true, okay? When you have, basically, this is the crux of it. This probability is not that intuitive given Bayes' theorem, okay? One way to get around this is to perform multiple tests, right? So that's going to be another homework problem that you'll find out is a way to curtail this. So not all hope is lost for drug tests. You just have to make sure to take multiple tests if you find it positive. Okay, so that is just another reason why probabilities are probably not as intuitive as you think. So let's go back and address the 3 reasons why probability should be easier to understand now. So 1, you can count how many events are possible in your sample space. 2, you understand definitions of set theory and how it provides the basis for probability theory. And then finally, you've updated your belief about the wrongness of your intuitions given your newfound grasp of Bayes' theorem. And now Bayes no longer laughs at you from his grave. So here are some more sources that will hopefully be clickable on the YouTube page. And again, you can always email me if you have any questions. All right, and good luck with your class.